Welcome to Study Loop.
Okay, so we're asked to calculate the period of two pendulums. One of them is a massless rod with mass m at the end, and the second one has a massive rod with an additional mass at the end. The rod having half the mass. Let's see. Rod having half the mass and the ball having half the mass. So here m is talking about the total mass of each system. In A, it's concentrated all at the ball. In B, it's concentrated, distributed over both the rod and the ball at the end. So we can make use of our handy formula for the period of a real pendulum, which is just 2 pi times the square root of the moment of inertia over the total mass m times gravity times the distance of the center of mass from the axis of rotation. So in this case, the end of the rod opposite the ball will be the center of mass. So we can go ahead and calculate A. A is a little easier. Okay. And it's pretty much as simple as remembering the moment of inertia. So for a point mass, call it PM, is just the mass of the point times d squared. And in this case, we're really talking about L, the length of the rod. So d is the distance from the point to the axis of rotation. And in this case, we can just look at our diagram and see that this length is L as given in the problem. So this is our moment of inertia. And from that, we can just plug in. T is 2 pi square root of m L squared over m g. D is also L here because the center of mass will all be here. There's no mass in the rod, so the center of mass is the same point as the entire mass is concentrated. So there's an L, and of course we're going to cancel out these. Masses also cancel out. So we're left with 2 pi times square root of L. I better open a new window. So we're going to call that the period T of A is 2 pi square root of L over G. Okay, and that is a formula that you can definitely look up somewhere. Pretty common. So for B, we are going to have a similar procedure. Basically, we just need to calculate the moment of inertia of this composite shape. Okay, with this axis for rotation up here. So how do we do this? In general, if you have the same axis of rotation between two different parts, or an arbitrary number of parts generally, they can add together. The moments of inertia will add together. So if we say this part has a moment of inertia I, call it I rod, and this has the moment of inertia I point, P, oops, we'll say the total moment of inertia for this system, IB, is I rod plus IP. It's important to note that, or remind you that the moments of inertia have to be measured from the same axis of rotation. So each of these is given as they're given in reference to an axis of rotation that's right here. So the only way to get this result to separate into these two parts is to consider axis of rotation at the end of the rod, first of all, and for the point, it'll have to be from a distance L away. So we remember IP from last part, right? IP is just the mass times the distance squared, distance from the axis of rotation, okay? Here, the mass at the point, remember, is only half of the total mass of the system, which we've already given the term m. So we're going to replace mass with m over 2, and we're going to replace d, in this case, with L. So we get m halves L squared for IP. As for the rod, you can look this up in a table. But the moment of inertia of a rod is going to be a third times the mass times well, you can call it L squared. In this case, we're also calling it L, but L is the length of your rod. So here again, we have to replace mass with 1/2 m. So in the end, we're going to get a 1/6 m L squared. Okay. Right, so we add these together, and a half plus a 1/6 is 2/3. So let's see. That means moment of inertia of this whole thing is going to be 2/3. Sorry, we were doing lowercase m. 2/3 m L. This comes from summing those two previous ones. Okay, so now we can go ahead and look at the rest of the terms in this. T is 2 pi square root I over m g d. So d is not L in this case. D is the distance from the rotation axis to the center of gravity. Okay, so we have a rod. Oops, I was drawing this in red. Red is where the mass lives. Oops. So D in this case, we're going to have to figure out where the center of mass is. So clearly the center of mass of the rod part is going to be in the middle. Okay. The center of mass of the point part is going to be at the point at the end. So this is black here. So this is L. This is L halves. And it's not the most rigorous way to do it. Really, you might want to compute an integral over these and figure out for yourself what the center of mass of the whole thing is. But you can argue that uh, since the rod has as much mass as the point, uh, you're going to take the average of these two. Um, you're going to take the average of the two centers of mass of these components with equal weight and find the middle of them. So the middle is going to clearly be right here, which is 3/4 L, right? So this is going to be the D that we have to plug in here, right? So in total, we're going to have the period is 2 pi square root. Okay, IB, we're going to plug in our 2/3 M lowercase m L squared over M times G, and then we're going to plug in our 3/4 L here. Okay. So we have 2 pi, our M cancels here, one of these L's cancels, and if I can divide whole numbers correctly, then we have, let's see, 8/9. I'll let you figure that out on your own. Double check me. 8. So we have 2 pi times root 8/9 times L over G. And this is for system B. And we're also asked which one takes longer to swing. So whichever one takes longer to swing will have a higher period. And so we have the 2 pi is the same. I'll write this as well to compare. TA is 2 pi root L over G. Okay. So the 2 pi's are the same. The factor of root L over G is the same, but TB is reduced by this factor of root 8/9. And so clearly this will have a shorter period, the second system, and will be faster swinging. So A is going to have the longer period. And in general, the thing with all the mass concentrated furthest away is going to have the higher moment of inertia. And a pendulum like that is always going to take the longest. So any real pendulum with weight distributed away from that endpoint is going to have a shorter period, is going to oscillate faster, back and forth. And that's the whole thing.